So what is a sequence? Now the word itself, sequence, means something in order, right? Something in order. Now in maths, sequence has the same meaning. It's just sequence is nothing but an ordered list. So sequence is like a list which is ordered. Now to give you an example, let's take number of not number let's say students in a class. Now this is an example, and the students in a class are, the first student is named A. For example, let's just say in a hypothetical situation, a student is named A, the second student is B, and then C, and the fourth student is D, and so forth, right? Now this is a sequence of students in a classroom. Now the important thing is that the first student is A, the second is B, the third is C, and the fourth is D. Now what I mean by that is that the first student should be A. I mean the position of A is fixed, right? The position of A is 1, the position of B is 2, position of C is 3. No, that what I'm trying to say is, in a sequence the position should be fixed. Now you cannot say that a sequence A, B, C, this is a sequence, let's say x1, and we have another sequence x2 which is B, A, C. These are not equal. You cannot say that x1 is equal to x2. They are not. And then let's take more of a mathematical example, an example which we would really use while studying or in an exam. So this is a set of natural numbers. A sequence is a function which is defined from set of natural numbers to x. It's a function. Now we let xn be f of n. Now you might not really get what I am meaning by this formal definition, so that's why we need to use examples. So let's just say, let's use another example which is 1 by n. Now remember, this acts like a function. Alright, let me just write it by side, that right now here just like we wrote earlier that x of n is f of n, right? So that means f of n is also 1 by n. This is like a function. Now this sequence is defined like this. So what would be the first element? When n equals 1, the first element would be 1 by 1 1. Now when n becomes 2, it will be 1 by 2. When n becomes 3, it will be 1 by 3, and so forth. So this is a sequence defined by 1 by n. Now let's take another example, which is x of n equals minus 1 whole raised to n, right? Now how would the elements of this sequence look like? How would this ordered list look like? The first element would be when n equals 1, it will be minus 1. When n equals 2, it will be minus 1 the whole square, which is minus 1 into minus 1, which is 1. When n equals 3, it will be 1 into minus 1, which is minus 1. And this would continue like this. This would go back and forth from minus 1 to 1. Alright, this is what it would look like. Now these are the examples of a sequence. Now just like I said earlier, this is like a function, so keep in mind like that. Now let's say that I want to plot I want to show you this sequence in a graph. This let's just say that I want to plot our first example on a graph. This is like a function, right? So we know that f of n equals y on a graph, right? So keep that in mind. So here is the graph, and the first element is 1, so it would be around when so this would be your n, your xn, and this would be this is your n and this is your xn. On your x-axis you have your n, and on your y-axis you have x of n. So this graph would look something like your first element n would be here, and x of n is 1, so we have a 1 and a 1. Would be simple. Now here n is 2. Now y would be 1 by 2, which would be somewhere 1 by 2 would be somewhere halfway between here. Now we have 1 by 3, which would be somewhere here, 1 by 4. So we can say that this list goes up to like infinity, 1 by infinity, or like 1 by 10,000. So we can say that as this goes on, the value of each element will go near to 0, right? Like 1 by 1000 is very much approximately like 0.0009 something, right? So it would reach tends to 0. So the graph would look something like this, right? It would really become close to 0. So we can say that I want you to just really get this into your mind, that when we plot the graph of this sequence, the sequence gets very near to 0, right? So we can say that the graph which looked something like this, it converges itself, right? xn converges itself to 0. xn converges to 0. Now when a sequence converges itself to a particular number, like we have here a 0, that's known as convergent sequences. Alright, so that's our next topic, which is convergence. we are talking about sequences, and let me give you another example. Now imagine I give you a sequence like this, where the first element is C, some another number C, the same number C, and C, and C. So this list is just filled with a lot of C's. So you can see that each and every single element of the sequence is the same. Now when each and every single element of the sequence is same, we call it as a constant sequence. Now that's a type of sequence in which we have all the elements as the same. Now other than that, let's go back to our old example, which was x of n equals minus 1 whole raised to n. We remember the elements of this sequence look something like this: minus 1, 1, minus 1, 1, minus 1, and 1. Now you can see that the elements are going back and forth between two same numbers, right? So the graph would look something like this. This is minus 1, this is 1, it would go here and here. So this is like moving in a to and fro motion. It's like an oscillation motion, right? So since this is an oscillation motion, we would call it as oscillatory sequence, right? Since this is these are oscillating between two different elements again and again, we call this oscillatory sequence. Well, how obvious, right? Now that we talked about how convergence work, now well, you guys can notice that an oscillatory sequence is not a convergent sequence. It should be as x of n, if you have a sequence x of n, as n tends to infinity, your x of n should go towards a particular number. It should go towards a particular number, and if this is satisfied, we would call it as converging sequence. Now let's try to give this one a formal definition, just like we gave it earlier for sequence. Now for convergence, let's see that let's say that we have a sequence x of n, and it is a real sequence. It is a real sequence for real, and we say that this x of n converges to some element, some number or some term x, and this x is an element of real numbers. This x is a real number, any real number. Okay, now you get this. This is a sequence, and as the x and the element goes on, the value of the one of the element of x and tends to go towards x, which is a real number, right? And we have another character term for any given epsilon. Just remember this epsilon, it's very important. For any epsilon which is a positive integer, there would exist an n, which is a number, which is an element of natural numbers, a set of natural numbers, such that for all k, I know this is very confusing, I have introduced a lot of alphabets, but I will try to make sense of it. We have a k which should be greater than or equal to the capital N. We will have x of k element of x minus epsilon comma x plus epsilon. I know that many of you are confused and didn't understand anything, which is normal. I can understand. It takes time to understand that one. Now let me show you this as a story. Let me try my best. Let's say that we have x of n, which is a sequence, of course, and the sequence has many elements, right? It has many elements. Now let's just like we said earlier, a convergent sequence, as n increases, or let's just say that n tends to infinity, xn tends to some number, and if it tends to a number, we call this a convergent sequence, right? We call this a convergent sequence. That's it. That's what we try to find using all those symbols. But let me just break it down for you. We have an xn, and it is this xn approaches or converges to a term or a number x, and this x is an element of real number. This is a real number. If there's a condition, this is only true if the condition that I'm about to tell you is satisfied. So xn tends to x, which is a real number, if for any given epsilon greater than 0, for any epsilon greater than 0. Now this epsilon is very important. Just let me just put it in the box for now. Just don't forget about it, right? Okay, so we have epsilon greater than 0, and now let's say that so since there is an epsilon which is greater than 0, and we also have an n which is any number, and that number is an element of natural numbers. Alright, we have already discussed this, that this symbol represents set of natural numbers. Alright, and and since this n is a set of natural numbers, we also introduce a term k. Now this k is important, and this k will be greater than or equal to some n, such that x of k. Now you see what we have done there. This n represents nothing but the nth term, right? This is the nth term, and when the nth term, we say that this is the kth term. This k term, when this k term is higher than or equal to some nth term, then the x of kth term, which is some number, natural numbers, any number, that x of k is an element of the range x minus epsilon comma x plus epsilon. Now what does that mean right now? Now let me draw a graph so that you can understand better. Right. Now we know that we have a sequence xn, and we drawn let's say that this is the graph of this sequence, and it approaches some point x, right? It approaches some point x. Keep that in mind. And this x is a real number. It's a real number. Now we take an epsilon, which should be positive. Now let me just place this on the side. Yeah, let it be here. And we also introduce an n, which is nothing, which represents the nth term. Alright, and this nth term, and we have our x, we have our k, which is also greater than or equal to n. Now let's say that this k is, we use this k for determining the term number. Now this xk should represent the somewhere. This xk would be after this k would come after this number, right? Now what specialty about this n is that this n comes after the function starts to converge. When some function starts to converge, it happens after the x takes a term k which is greater than or equal to n. I hope you understand that. This x starts to converge when it is on a term, kth term, which is k which is greater than or equal to n. So n is like a limit. N is like a limit after which the sequence starts to converge. I hope you get that. So let's just say that for here example, let's say half, this is where the n is, and after when here the k takes a value greater than n, the function starts to converge, right? It starts to converge. In this graph it starts to converge to 0, right? So that's what is happening. And your x of k is an element of x minus epsilon comma x plus epsilon. Now let's just say that this xk would be part of a range. So epsilon would be some very small, which would be 0.001 or something like that. So let's just say that it would be here, right? This is your x of k minus epsilon, and this is where your x is, and this is x of k plus epsilon. Alright, now your x should be somewhere over here, right? So this just tells that as a converging function becomes bigger, a converging sequence as it goes on, it gets converging, it gets converged to some point, and that x is found somewhere between this range, x of k minus epsilon and x of k plus epsilon. So okay, so we have a small mistake here, which is just that it's just x, right? It's just x plus k and x minus k. So what does that tell you about x? Now x is the absolute value. The x is where the point of convergence, right? This is the point that xn is approaching. Now your element x of k, after n it starts converging, would be somewhere between x plus epsilon and x minus epsilon, and this epsilon is nothing but an error. Alright, so I guess that's about convergence, and this is a start of a new series about mathematical analysis, and this was our first topic, which is about sequence and converging sequences, and in the next class we will do some problems. So until then, see you.